everyone. Today we are trying to teach you modeling and control design for drone systems, flying drones. And this video is taken regarding with the European Union Erasmus Plus Key Action 203 project, which is named as Developing Novel UAV Education Set and Training Curriculum in order to catch state-of-the-art technology. This is in collaboration with Romania, Technical University of Bucharest, and RGS University and TU Berlin. So here we will first try with Mambo drones, which is very nice smart toolkit in order to understand the dynamical and kinematical behavior of multi-rotor drones, and then testing your flight control algorithms. First of all, I would like to try with the flying mentality behind of these drones. These drones are sometimes modeled in cross configuration, sometimes in plus configuration, and there are some pros and cons in both ways. Here generally we are using a cross configuration approach in order to obtain my kinematical and dynamical equations. We will keep in deep on these on these topics in the upcoming videos. Here I would like to shortly tell about how these tools are flying. So as you have seen, there are 4 rotors in this mini drone, and each counter-rotating rotors or counter-rotating parts are rotating in the same direction. That means these rotor 1 and rotor 3 rotating on the right hand side. In this case, this rotor 2 and rotor 4 is rotating counterpart, counter-rotating. That means they are on left hand side rotating, and their torque levels on these rotations are affecting their roll, pitch, and yaw actions. So yaw actions, that means if they are rotating in the same torque levels with the aforementioned rotation and counter to rotation selections, they are doing hovering. If these counter rotating parts obtained with different level of torques, that makes you yaw action to left or right. And then if counter rotating parts, rotor 2 and rotor 4 in these 2 rotors are in the same torque level, however these 2 rotor 1 and rotor 2 on the different rotation level, that means torque level, then they provide you some pitch action to up and down, and roll action is same when you are using your rotor 2 and rotor 4 parts. Today, as you have seen, these are how you are dynamically or flight mechanically provide a flight on these things. As soon as you provide same level of rotation and torque, then you hover, and then you do waypoint navigation with these drones. Today we will test our manual hovering and then autonomous waypoint navigation algorithm. Shortly show you at the end of this video, and share you our capacity as declaring the content of our chapter 1 study in these Erasmus Plus Key Action 203 project. So as I said, up until now, they are very nice tools, nice toolkits, and we are planning to do a lot of algorithms. In the upcoming video, we will show you how we build up a collaborative flight, rigid formation with these two tools. And there will be a lecture in the upcoming videos as well. So let's build up a flight, how we start up and then to waypoint navigation with these. Let's start. So now we are testing this manual takeoff and then waypoint action in order to see the better reaction of your nested control system. Generally in these systems there are different approaches. One of them is explained as successive loop approach, generally used to the control design for flying vehicles. Now for multi-rotor drones there are nested loops, that means inner and outer loop. Outer loop is taken the position requirements and then convert to the angular requirements, because these systems are work with these angular requirements, angular inputs, and then these angular inputs converted to torques of yaw, roll and pitch, and then thrust action. Now we will test this flight, which is with research assistant Rahman. Now power is taken care of, and then going back and forth with this control inside. Yes, thank you very much, this is very good. Now we can manually landing. Thank you very much, this is perfect.